Would you like anything to eat? Nope, I'm busy. What happened, honey? You sound disappointed? Yeah, this magnifying glass can't zoom in more. Why? Isn't it enough? No, no, I need more. Well, fear not, mortal, for gravitational lensing exists. All you need for this make it home 3-step easy peasy DIY gravitational lens is an object of immense mass. For example, your favorite galaxy cluster. That's actually just about it. Now just follow the simple 3-step process. Place this object really far from you and travel a good distance from it. Yeah, that's just about it. What's gravitational lensing again? Wait, you don't know? Bro, I'm a botanist, not an astrophysicist. Oh, anyways. So, light travels in a straight line, right? Right? Well, kinda. There are, of course, factors that change the direction that light travels in. But first, let's understand why light travels in a straight line. So, there are two main ways that energy is transferred between two locations: particles and waves. See, there's also something you need to know about our little friend, light. It's kinda indecisive. Sometimes it wants to act as a particle and sometimes as a wave. However, for the sake of explanation, I'll consider its particle form: photons. See, photons are point particles, which means they have no length, height, or breadth. They exist as a single point with no mass. So, what really are they? They are pure energy. Unlike electrons or protons, they don't have any charge, but just energy. In layman's terms, they are neutral. See, because they have no charge, they are not attracted to any charged surfaces. So they travel straight. And because they have no mass, they're not affected by gravity. Although, do remember that light is affected by gravity in relatively larger amounts. I'll explain that later in the video. So this reason shows that light will travel in a straight line all the time, right? Well, of course, matter and gravity do not exist. See, matter has multiple ways to affect the direction that light travels in, but it can be boiled down to the photons interacting with the matter through absorption and the re-emission of energy in the form of light or photons. This is a small diagram for said phenomena. Then comes gravity. See, gravity, according to Einstein's relativity, is not a force between massive objects, but rather a curvature of space-time caused by the presence of mass and energy. A little too complicated for you? Well, I'll take an age-old example. Think of space-time as being a simple piece of cloth with nothing above and nothing below. Once we place an object on it, the cloth is sure to bend. This is general relativity and essentially gravity. Now, if we try to make an object cross the cloth through the bend, it will curve around the larger object, right? This is how gravity works. However, now is a little roadblock. Doesn't light have no mass at all? How is the direction of light being changed by gravity at all if gravity only affects objects with mass? Well, this is a completely valid question, but the answer is nonetheless simple. See, this is the difference between Newton's gravity and Einstein's. Newton's formula only considered objects with mass, and his definition of it being a force said that it would only affect bodies with mass. Einstein, on the other hand, said that it was a curvature
in space time, and thus it affected everything that went through the space time, whether it had mass or not.
This bending of light is similar to a lens, allowing this phenomena to help us peek at objects insanely far away. In fact, in the March of 2022, the renowned Hubble Space Telescope was able to take an image of a star by the name of Earendel, 12.9 billion light years away, using this very phenomenon. This means that the light we see from Earendel is 12.9 billion years old. Cool. Where do I buy one? You can't. What? Then how do I use one? To be honest, gravitational lensing is on a much larger scale than your day to day flower observations, so I think you'd just be better off using this.